Okay, can you see my screen? It should be working. Okay, so hello everyone, my name is Daniel, and today I'm presenting UNCHARTIT, which is an interactive framework for program recovery from shards. And UNCHARTIT is the result of joint work between INESC-ID, Technique Lisboa, and Carnegie Mellon University. And so to start, with a small motivation, consider the following table and bar chart. This bar chart graphically represents a summary of the table, meaning that what I did was apply a sequence of data transformations to the table to obtain the chart. Now, suppose that we need to recover those data transformations, the program that maps the table into the bar chart. For this example, this is just a table of flights with 3 columns, the ID of the flight, the origin, and then the destination. And here what I did was I started by filtering all the flights that go to Lisbon, and in this way we got rid of the second row. And after that, I counted the number of flights for each origin, and we get this table here with 1 flight from Berlin, 1 from BOD, and 2 from Geneva. And finally, I just converted the table into a bar chart. Okay, so what UNCHARTIT can do is retrieve this sort of data transformations from pairs of table and chart. And for this example here, this is the program that UNCHARTIT returns. It's a 4-line program in the R programming language. And some practical applications for this, with UNCHARTIT, you can recover old programs that you no longer have access to, or programs that were written by somebody else that's not available at a time. And with this, you can apply the program to new data and you get a new chart, and all of this without writing a single line of code yourself. Okay, so how does this work? Here's a small overview of UNCHARTIT architecture. It has 4 main components. The input of the system is, as we've seen earlier, the input table and the chart. And I'll get to the details of each of these components. The first component is the data extraction. And in the data extraction, what we want to do is we want to interpret the chart image automatically. We essentially want to go from pixels to numbers. For instance, for this chart, this is the table that we get. And we do this using 2 different methods. The first is using web plot digitizer, which is a semi-automatic tool, meaning it requires more input besides the chart image to interpret the chart. And we also adapted one of the efficient nets, which is a state-of-art convolutional neural network for a fully automated approach. But anyway, regardless of the method that we use to extract data from the chart, there is always a mismatch between the real table that's underlying the chart and the extracted table, because this is a really hard problem. We are literally going from pixels to numbers here. And so you can see here on the left, on the right, we have 2 tables, the extracted table, and that one was obtained using web plot digitizer, and below it is the real table underlying the chart. And you can see that the bar labels are missing, and there are some numerical imprecisions on the numerical values of the extracted table as well. And to show you a small demo of these tools, here's the web plot digitizer user interface. So this is semi-automatic, as I've said earlier. I have already loaded the chart image. Now it's asking me to select 2 points over the vertical axis on the chart. And this is why it's semi-automatic. It requires more input besides the chart. And now it's asking me to provide it with the actual values of those points on the vertical axis, which I did. And now after some tuning to the parameters of the extraction algorithm, it finds the bars and extracts the values automatically for me. So here are the bar values. You can see there are some numerical imprecisions, and it also does not extract the bar labels automatically. So this is the semi-automatic tool, web plot digitizer. And for the efficient net approach, which was the approach that we adapted, we only need to provide the actual chart image and also the maximum value of the vertical axis, but that's the only input it requires. And now it should identify a bar chart with 3 bars and their respective values. So here are the here's the output. So there are the 3 bars and the values that it extracted. There are some imprecisions, but it can do it automatically. Okay. So after you finish this step, the data extraction, we get into the second step of UNCHARTIT's pipeline, which is the candidate generation. And in the candidate generation, the input is, in this case, the original input table and the extracted table that we got from the previous step. So here's one example of such input. And here what we want to do is to find a program that maps the input table into the real table that's underlying the chart. But note that the real table and the extracted table are not the same thing. As we have seen earlier, the extracted table is only an approximation of the real table underlying the chart. So what we do is we use program synthesis to enumerate multiple candidate programs, and we generate multiple candidates and decide to keep or discard a given candidate by running it on the input table and comparing the output shape of that program to the output shape of the extracted table. And I'll show you what I mean with some examples. So here's one program that UNCHARTIT generates and the respective output. You can see that the output table has 3 rows and 2 columns. And in the extracted table that's on the bottom right, there are also 3 rows and 2 columns. So we accept this program has a good candidate. And here's another example of a program. And in this case, we also get a table. The output of the program is also a table with 3 rows and 2 columns. So we accept it as a candidate because the output shape matches that of the output shape of the extracted table. And a final example here, a third program that also outputs a table with 3 rows and 2 columns. So we accept all the 3 programs as good candidates. Okay, and after we finish the candidate generation step, we get into the candidate ranking that takes as input the candidates we generated in the previous step. And our motivation for this step is that there are usually many candidate programs that satisfy that criterion we had defined earlier of the matching output shapes. However, the contents of the actual tables, the contents of the output might differ. So what we do is we use an error metric to rank the programs. And one example of an error metric that we use is the mean squared error, like this. And to show you one example, so here is the original input table, and one of the programs that UNCHARTIT generates, we just need to compute the program's outputs on the input table, and we get this table here. And then to calculate the score of the program, in this case, we are using the mean squared error. So we use the last 2 columns of the extracted table and the program and the program's output to compute the score of the program. So here you can see we are doing a row-wise subtraction, and then we sum everything together, just as a standard mean squared error approach. And we do this for every single candidate that we generate. So for the 3 programs I showed you earlier, these are the scores that we get. And after that, we order the programs according to the scores. So here we actually have a tie. So the top ranking programs have the same scores here. They both rank 1, and the third program ranks 3 because its score is slightly higher. Okay, so finally we reach the 4th component of UNCHARTIT's pipeline, which is the program disambiguation. And in the program disambiguation, what we want to do is to distinguish the best candidate programs that we got from the previous step. And we do this because the top ranking program is not necessarily correct, but it is very likely that it ranks on top ranking programs. So what we do is we select the top ranking programs and interact with the user. We ask the user questions to ascertain that we always return a correct answer. And we do so using 2 interaction models. The first is the options interaction model, in which we ask the user multiple choice questions. And for the yes or no interaction model, we ask the user yes or no questions. And so to recall the examples I showed you earlier, so this is the correct program. This is a program that counts the number of flights that go to Lisbon. So this is correct. And the other 2 that I showed you as well are incorrect. This one is filtering the flights that don't go to Geneva, so it's incorrect. And this one is also nonsense because it's filtering by ID. And so to show you an example of a question that UNCHARTIT generates, for the yes or no interaction model, UNCHARTIT automatically generates this small test case. And here the user needs to look at the input table that UNCHARTIT generated and has to decide whether or not the computed output is correct for the program he desires. And in this case, remember that we want to count all the flights that go to Lisbon. So here in this table, there's only one flight that goes to Lisbon. So this chart is incorrect. It should only have one bar. So the user answers no. And after these, UNCHARTIT discards one of the programs in this case. And we get into a second interaction round, and then UNCHARTIT generates again a new small test case. And here the user also has to decide whether the computed output is correct or not. And here we have all the flights go to Lisbon, so the bar chart is correct. The user answers yes, and the correct program. And for the options interaction model, the interface is very similar, but in this case, instead of asking a yes or no question, we are asking the user to pick the correct outputs for the generated inputs. And here what UNCHARTIT tries to do is to find an input that distinguishes as many programs as possible in one round. So here we have 3 programs, and UNCHARTIT can find an input that distinguishes all 3 programs. So the user only has to answer one question. And so the correct one is that chart. The user answers that, and the correct program is returned. Okay, and to generate these questions, we actually use 3 different methods. And the first method that we use is fuzzing. And in fuzzing, what we do is we randomly generate inputs for some time, and then return the best input that we find. And the best input depends on the interaction model that we are using. So for the options interaction model, I said earlier, we want to find an input that distinguishes as many programs as possible in one interaction round. And for the yes or no interaction model, we want to find an input that discards exactly half of the programs in each round of interaction. And we also try to solve this problem formally using a combination of program verification and MaxSMT. So we encode the programs in a formula, and then we also encode an optimization formula to generate the best possible question for each interaction model. Finally, we have an hybrid approach that combines the first 2. We use fuzzing for the first rounds of interaction because it is fast, and we finish with the combination of program verification and MaxSMT for the last rounds because it also gives us some theoretical guarantees regarding the optimality of the questions. And there are details on the implementation and encodings on the paper. And so here is a small demo showing UNCHARTIT user interface. In this case, we're trying to distinguish the top 10 ranking programs. So this is the first question that UNCHARTIT generates. The user has to answer yes or no. In this case, I answered no. And UNCHARTIT generates again a new question. In this case, it is correct. So we, because we want the flights that go to Lisbon, in this case, we have 2. And one final round of interaction. And since there are no flights that go to Lisbon in this case, we have an empty chart. So the correct program is returned after the answer. For the options interaction model, the interface is similar. But again, we get the multiple choice question this time. So here is the input that UNCHARTIT automatically generates. And in this case, it can distinguish all 10 programs in one round of interaction. So I answer, and we get the correct program here. Okay, so regarding implementation, UNCHARTIT integrates several existing technologies I have mentioned earlier, the web plot digitizer and the EfficientNet for the data extraction. And for the candidate generation, we use the Trinity framework, which is a program synthesis framework for data science. And for the program disambiguation, we use the C-bounded model checker, CBMC, and also a max stat solver, which is OpenLinux BPS. For benchmarks, we collected 50 benchmarks from Kaggle, which is a website for data science. And each benchmark is comprised of a pair table and bar chart. And they correspond to real tasks. And on average, each of the tables we collected has roughly 71,000 rows and 18 columns. And we have our bar charts with up to 15 bars. Regarding the percentage of benchmarks solved. So we actually only need 3 minutes to find the correct candidates for most of the benchmarks, for 92% of the benchmarks. And this bar chart shows you the percentage of benchmarks in which the correct candidate ranks among the top 1, top 3, and top 10 ranking programs using the web plot digitizer approach and the efficient net. And here the efficient net gets a slightly less it solves less benchmarks because it is generally more imprecise, but it also requires less input. So there's always a trade-off. And for the percentage of benchmarks we successfully disambiguate, we can successfully disambiguate the top 10 ranking programs in 94% of the ambiguous benchmarks. And using the 3 methods that I mentioned earlier, so with fuzzing, we can disambiguate, I think it's roughly 84% of the benchmarks. And the best approach, which is the hybrid, we get the 94%. And this bar chart here on the right shows you the average number of questions that we have to ask the user to disambiguate the top 10 ranking programs. So for the options interaction model, we just need to ask on average 1 question. And for the yes or no, 3 questions is usually enough. Some final remarks. Our main contribution is a first automated tool for program synthesis that deals directly with chart images. And we also proposed program disambiguation methods for program synthesis that can be used in a variety of scenarios. And we have extensive experimental results on real-world benchmarks. For future work, we would like to add support to other chart types. Our tool is currently limited to bar charts. And we would also like to add support to end-round charts. And UNCHARTIT will be available eventually here. And that's everything. Thank you for listening. I can answer any question you might have.
Thank you, Daniel. And again, let's thank our speaker virtually. And we have time for 1 or 2 questions. So again, please use the raise hand button or type your questions into the Huba app. Okay, I have 1 question, Daniel. So the examples of programs that you showed during your talk look fairly small. They're like straight lines, long. I was just curious about the programs that you generated or synthesized over the benchmarks. Were they similarly sized or are they a little bit larger?
Yeah, they're usually up to, I think it's 5 or 6 lines of code. And that's actually the standard in this sort of data science domain, because the search space does increase very quickly with each line of code. So those are real programs. So it's usually up to 5 or 6 lines of code in this domain. Yeah.
Okay. Cool. Thanks. All right. Doesn't appear to be any other questions from the audience. I guess I have 1 more question. Have you shown the synthesized programs to your users and just ask them, would they like to continue to modify the program, or do you sort of intend that these programs will basically be sort of hidden from those users?
Yeah, so the programs are supposed to be hidden from the users, and we actually did not do any user studies, so we simulated the user here, but the user is not supposed to directly interact or look at the programs, because we're assuming here the user has low programming knowledge and does not know what the programs are doing really. So yeah, that's one of the assumptions we make.
Okay, thank you. Okay, I guess if there are no more questions, then we'll end the last talk. Thank you again, Daniel, for your great talk. And so that's that was the last talk. So this is the end of session. Thank you everyone for coming, and we'll enjoy the rest of the conference. And then with that, we'll officially conclude this session.